All right, we're going to talk about exponential modeling now. Exponential functions are ones that grow or decay by the same relative amount or percent. Remember from earlier, relative amount referred to a constant percent rather than a constant amount that was growing or decaying. The formula for an exponential growth or decay is Q equals Q naught times 1 plus R to the t power. Now Q represents the amount at a given time. Q naught would be the initial value when at time 0. R is the growth rate, the percent of some rate, and T is the time. All right, the 2010 census found a U.S. population of about 309 million with an estimated growth rate of 0.9% per year. Write an equation for the U.S. population that assumes exponential growth. Use this to predict the population in the year 2100. Okay, so let's start with what do we know? I know that the starting population, we're defining the starting population to be 2010, was 309 million. So I'm just going to use 309 and just remember that this is in terms of millions, so I don't have to keep all those zeros handy. And then I need a growth rate. Well, it's 0.9%, which is a decimal, is 0.009. And so our formula would be Q equals 309, 1 plus 0.009 raised to the t power. Okay, in the year 2100, so answer that question. Well, how much time has surpassed then? So for 2100 minus 2010, we're only looking at 90 years. So to find the amount at that moment would be 309 times 1.009 raised to the 90th power. Okay, now this is one you got to be careful of when your calculator. So I'll kind of walk you through how to do this. All right, so for me, I type in the number first and then raise it to that power. So 1.009, and I'm going to raise that to the 90th power. And then whatever that result is, I'm going to type that by the 309. So you should want to start inside the parentheses first and then go out. Okay, so I would predict that's about 692 million. Okay, sometimes we want to look at a graph of these things. The nice thing is with exponential growth, we have enough information. Usually it's pretty quick to find doubling times and things like that. So when we graph this, we want to plot the points. We're going to go 0 and the initial amount. And then I want the double time. And I want 2 times the initial. And if I can figure out the triple time, I'm sorry, 2 times the double. Then I want 4 times the initial. And 3 times the triple. Sorry, 3 times the double, which would mean how times it took to do that 3 times. And then that would be double the 4, so I get 8 times the original. Okay, so in a graph, what that would look like when I have this, so here's my 0, here's my initial amount. Somewhere I'm going to have the double time listed, and 2 times the initial, so I'll have a point here and I'll have a point here. And I'll have 2 times the double time. And then this is going to be 4 times the initial. So I'll have another amount. And then I'll have 3 times the double. And then I'll have 8 times the initial. So there's another point. So when all said and done, it should sort of resemble this little grid here. Now these little extra lines I just drew in is just so we can visually see how that works. And so this would be an example of exponential growth. If the graph actually represents decay, it's kind of similar. So we start off with the initial, but then I got half time instead of double time. So that would be the initial amount divided by 2. And then I got twice the time it took for it to get half. And that would be the initial divided by 4. And then 3 times the time it took to get half of it. And that would be the initial divided by 8. So usually after that it's pretty obvious what's going to happen. So looking at a graph, and then here's 0. Now this time I'm getting smaller, so my initial amount would be up top there. And then I would have the time it took for half of it, which would give me sort of halfway in the middle would be Q naught over 2. So those should kind of line up. Then 2 times that half time, which would be another half of this Q. So this time it would be Q over 4. And then 3 times the half time, which is another half of the last one, so that'd be initially over 8. And so with all those points plotted in, I could see a real quick pattern. I could sketch the graph in like that. Okay, exponential functions come in a couple of different forms. So we've seen the past couple of sections, we've seen a few of this, so I just want to go back and remind us. If, for example, we are given growth or decay rate, R, then we want to use this form. So Q equals Q naught 1 plus R to the T. If we're given the double time, then we want to use, so the time it took for it to double, then we want to use Q equals Q naught times 2 T over the double time. If we're given half time, the time it takes for half of something to show up, then we want Q equals Q naught 1/2 T over T of half. So based on what they tell us, we can then write an equation around that.